This video is about the mathematical background for the linear system and control class. So we'll start with the vectors since in the state space representation we'll talk about the system states given by a vector and also the ABCD matrix in the state space representation. We'll talk about it on which will have matrices. So we'll talk about some of the basic operations for the matrix and vectors. Okay, so first of all, what is a vector? So vector is we can consider as a stack of numbers written in column or row. Okay, if it's written in the column, so two brackets, and I put numbers inside 1, 2, 3. So this will be just a column vector, and row will be just write a 1, 2, 3 as a row. So it's a row vector. So this is a column vector, row vector. Vector is just by putting a set of numbers together as a row or a column. Okay. So matrix is a little bit general. We have more than one row and typically more than one column. Okay, so you can sort of see the vector is a special case for the matrix. When you have only one column, is called a column vector. The matrix becomes column vector. When we have only one row in the matrix becomes a row vector. Okay, so the matrix is given by A, let's for example, A2 times 3. So typically don't write the size out directly. So the size is given by the number of rows times the number of columns. For example, here is 1, 2, 1, 4, 2, 1, 4, 2, 5, 3, 6. So typically you read the number according to a row, and first row, second row, and a third row. Okay, you don't normally we don't read as 1, 2, 3, 4, 5, 6. Okay, so the first row here we have row 1, row 2, and row 3, and we have column 1 and column 2. So we have 3 rows and 2 columns. So here is 3 times 2 because this is 3 rows and 2 columns. So we call this is 3 by 2 matrix. Okay, so which means I have 3 rows and 2 columns. Okay. And also you can also specify each row and the i's and the j's entry of this matrix, which is i's row and j's column. Okay, we give a specific name. For example, the first row and the first column will be 1, 1. The first row and the first column of this matrix is given by 1. And the first row and the second column is given by 4. Okay. So for the vector, there's one fundamental part we talk about the property for the vector is called a vector norm. Vector norm talks about a map from a vector to a non-negative scalar, satisfying two basic properties. So vector norm talk about a property of vector. This is a property of vector. So it maps from the vector itself to a non-negative scalar. So satisfying this following 3 properties. The first one is this: if I represent the vector norm as fx, okay, typically the norm is written by this form: is you put 2 vertical lines before this vector and 2 vertical lines after the vector. This represents the norm. So if I represent the norm as a function of fx, okay, typically it's a function of fx. So it maps from the original vector to a non-negative scalar. So here R inverse means negative, real and negative value, and I put a bar means non-negative, a non-negative scalar. Okay, so maps from a vector to a non-negative scalar, and satisfies 3 properties. First property is this norm is always non-negative, and this norm equals 0 if and only if this vector is 0, which means every entry in the vector is 0. Okay, typically when we talk about the vector norm, we talk about a column vector, not talking about a row vector. Okay, the first property, okay, means it's non-negative, and if it's 0 if and only if the vector itself is 0, meaning that each entry of the vector is 0. The second property says f of alpha x is the absolute value equal to absolute value of alpha times fx. So alpha is a real number, which means if I scale this vector by a number, okay, it can be positive, it can be negative, but since the vector norm cannot be negative, so I just put the absolute value of whatever scalar I give. So this scalar, real number, could be negative, could be positive, and times the norm of the original vector x. Okay, the the last one is fxy x plus y. So x is a vector. Okay, this is a vector, this is another vector. You put them together, the norm of the vector sum is less than or equal to the norm of the each individual one, fx and fy. So this is called inequality. You can see it's a convex condition. Okay, any function that satisfies this three property can be defined as a vector norm. Okay, so one of the typical type of norms that people use called p norm. So p norm is a general norm. So it is defined as x of p norm. You put a subscript p rather than the standard norm definition or notation. You also put a p as a subscript, which means p norm. P norm is given by it's sort of the, let's see what's inside this one. The inside here is a number summation. So this means that this is the summation. Okay, so summation, what is computed as a sum? So you first compute the absolute value of each number. Okay, assuming this x is given by x1, x2 into xn. So you first compute the absolute value of that each individual number over here, and you get a p power of it. Okay, p's power of it. Okay, then you compute the sum for each one. You compute the absolute value, you compute p's power, and then compute the sum. After computer summation, you do the power of 1 over p. Okay. All right. So it looks a little bit complicated. So let's give an example about a p. So this p can be any positive, non-negative number. So you can do that. This will be a valid vector norm. Okay. So when p, let's give a few examples to see what is the exact form of the norm. Sometimes it looks pretty simple. Okay. So let's say, what if p is 1? Okay, this is a very special one. Okay, if we do this one, so this is called a 1 norm. This is also called 1 norm. So we replace p by 1, so it's 1 norm is equal to, if I replace everything p by 1, so this is absolute value of xi to the p is 1 to the 1, which is exactly 1, so I can ignore it. So which is just absolute value of each entry. You compute the sum, and then you take a power. This also is a 1 over 1. It's still 1 over here, right? So you just can ignore this. So because x to the 1 is still x, okay? Or like 2 to the 1 is still 2. So it doesn't really matter, okay? So it's exactly the same of the absolute value of each entry of the vector. This is called 1 norm. 2 norm is given by, notation wise, given by the 2 norm, and you put a subscript of 2. So which is, if I use the same way we computed this norm, we just replace p by 2. So we have the summation of I from 1 to n xi absolute value to the squared. Okay, then like compute the sum, and then the power of alpha, the outside power is 1 over 2 because p is 2, so 1 over 2. Because 1 over 2 is, for example, I do 2 1/2 is just the square root of 2, right? 1/2 is just the square root of it. So it's just a square root of summation from I to n xi squared, which means it's a square of each entry, and you take the sum. After you take the sum, compute the sum, you take a square root of that. That's the 2 norm. Okay, last one is infinity norm, which means when p goes to infinity. Okay, so here we replace p by infinity. The computation will be the same. A little bit complicated here is, I have here xi to the p. I take a limit as p goes to infinity and take the power of 1 over p. Okay, this one, okay, is just equal to maximum of absolute value of xi, and for each one. Okay, it's also the same as the square root of the maximum of I xi squared. Okay, I don't want to talk about too much detail about why that's the case. You can sort of consider this. If you have, let's say, I give example here, xi is 1, 2, and 3, for example. Oh no, here's x. Okay, so apparently I have 3, right? So according to here, the limit, the x infinity is, according to the definition, is the limit of p goes to infinity. I have here, I write out a summation. Okay, it is 1 to the infinity plus 2 to the 1 to the p, 2 to the p plus 3 to the p, because I ignore the absolute value because they are positive, right? To the p, You saw that now. What you can do, you can divide this one infinity over here. Limit p goes to infinity. So I can divide everything by this should be 1 over p. So inside, what can do? I can do is I do 1 over p plus 2 over p plus 3 over p. So first of all, I divide by 3 over p, 3 to the p's power, and times 3 to the p. But that's the same thing. It doesn't change anything because they will cancel out. This limit of this guy, p go to infinity, I can just divide this by into 2 components. One is 1 to the p plus 2 to the p plus 3 to the p, right? Divide by 3 to the p. And 1 over p. And this is 3p, 3 to the p. This is 1 over p, because this actually will cancel out. This is just the same as 3. Okay? So this guy you do over here, because as p goes to infinity, let's write over here, put it over here as 3. If I do over here, this one, it will be limit p go to infinity. This is 1 over 3 to the p's power, plus I can divide this, I can write it as 3 different terms. Okay, it's 2 over 3 to the p's power, plus 1 to the p's, and 1 over p times 3. So this guy will go to 0. As you can see, this guy will go to 0. This guy goes to 0, and this guy goes to 1. It's to be 1. So 1 to the p is still 1 to the p is still 1. That's why this becomes 3. That's the maximum value you have. You can always divide everything by the maximum absolute value of this one. That's why you get it as 3. Okay, this is the maximum value of this number. This is sort of idea why you can see this. The infinite norm is just the maximum value of the absolute value of each entry. Okay. All right. Now let's take a look at some example how to compute the p norm. And when we talk about the p norm, what is the p norm? What is 1 norm? What is p norm? Or 2 norm? What is the infinite norm? Okay, let's talk about one example. If I give x which is -3, -1, 0, and 2, okay, let's compute what is 1 norm, what is 2 norm, what is the infinite norm. So the 1 norm is just given by the absolute value of each entry, then you compute the sum. Okay, that's what this says. Okay, so it's just you compute the absolute value of each entry. Okay, then you compute the sum. Okay, pretty straightforward, just given by 6. The 2 norm is given by the square root of the square of each entry. Okay, so it's -3 square plus -1 square plus 0 square plus 2 square, and they take a square root, which is just square root of 14. So the infinite norm is just you take the maximum value of the absolute value of each entry. So the maximum value of all the absolute value of each entry, which is absolute value of -3, absolute value of -1, absolute value of 0, absolute value of 2. So this is just 3, 1, 0, 2. So the maximum of this will be 3. So that's why this is infinite norm will be just 3. Okay, quite straightforward. The next concept is linear independent vectors. Okay, so here's the definition of linear independent vectors. So if you give a number of vectors, x1, x2, xn, so here x1, x2, x, they are vectors, they're not scalars over here. So don't be confused by here. So here I mean that each one is an entry, but here each xi is a vector. Okay, so x is vector size n by 1, and assuming it's a real vector, it's not does not include complex numbers. Okay, so if I do a linear combination of these vectors by assigning different weights for different vectors, alpha 1, alpha 2, alpha n. So alpha 1 plus x1, alpha 2, x2 plus alpha n, x1 is equal to 0 n times 1, which means this is a 0 vector. Okay, if I set it to be 0 and I try to compute what is the actual value of alpha 1, alpha 2, alpha n, if this one means I can only find one solution, which is alpha 1 0, alpha 2 0, and alpha n they are all 0. If the only solution to this linear equation is alpha 1, alpha 2, and alpha n they all equal to 0, okay, here alpha 1, alpha n they are real scalars, then we call x1, x2, xn are linear independent. Okay. So for let me give you an example what we mean by linear independent. So let's say if I have vectors x1 which is 1 0 0, x2 0 1 0, x3 0 0 1. So are they linear independent? Okay. So to check the linear independent, we have to compute. You can compute this alpha 1 x1, alpha 2 x2, alpha 3 x3. We set to be 0 0 0. Okay. You want to calculate, okay, what are the solutions to this equation? What kind of solution can we find out? Does that mean all this alpha 1, alpha 2, alpha 3, they all equal to 0? Okay, let's find out. So by writing out x1, replace x1 by this, x2 by this, x3 by this, we can get x1, alpha 1 times x1, alpha 2, x2, alpha 3, x3, and we do the multiplication, multiplies of these numbers. We have alpha 1 times 1, alpha 1 times 0, alpha 1 times 0, so it's alpha 1, 0, 0. Similar here is 0, alpha 2, 0, this is 0, 0, alpha 3. If I set it at 0, 0, 0, so if you find a solution, the only solution is alpha 1, 0, alpha 2, 0, alpha 3, 0. Okay, because if this one is the same as alpha 1, alpha 2, and alpha 3. If this one equal to 0, 0, which means each entry should be 0, 0, 0. It should be 0. Okay, so yes, it's linear independent. So let's give another example. Let's say x1 is 1, 0, 0, x2 is 0, 1, 0, x3 is 0, 1, 1, 0. Are they linear independent? Okay, we can use the same approach. So alpha 1 times, let's say, assume we have alpha 1, alpha 2, alpha 3, so we multiply this one, each vector by its corresponding scalar, alpha I. So alpha 1 times x1, alpha 2 times x2, alpha x2 plus alpha 3 times x3, which is 0, 0, 0. Okay, so then we do the multiplication of each entry of this vector by this scalar. Okay, so which means we have here f1, 0, 0, 0, alpha 2, 0, this is alpha 3, 0. Okay, so this one is the same as, okay, if you put each entry together. So the vector sum is entry-wise sum of all the vectors. So it would be alpha 1 plus 0 plus alpha 3. So this is alpha 1 plus alpha 3. So this is 0 plus alpha 2 plus alpha 3. So it's alpha 2 plus alpha 3. And this is 0 plus 0 plus 0. Yeah, this is 0. Okay, so which is this guy has to be 0. Okay, if you do over here, we have alpha 1 plus alpha 3 is 0, alpha 2 plus alpha 3 is 0. So 0 is equal to 0 is already true. Okay, so if you find this, we can find the solution. Of course, here, yeah, we cannot say alpha 1, alpha 2, alpha 3 are 0. Of course, this is always a solution. Alpha 1, 0, alpha 2, this is always a solution, because if you put a 0, 0, 0, of course, this is a solution. But you can find more than that. You can find more solution. For example, if I said alpha 1 is negative 1, alpha 2 is negative 1, alpha 3 is 1. Yeah, this is satisfied, which means this is still 0. The sum will be 0. Yeah, which means this is not a unique solution to this equation. Okay, which means it's not linear independent. Okay. All right. So to summarize, in order to check if system is linear independent, you can use this as a typical way to verify if a set of vectors are linearly independent. As a matter of fact, you can also see over here, because x3 is equal to x1 plus x2, right? If I look at it, because this guy sum of these two will be equal to x3. That's why it's not linearly independent. You can also interpret it in that way, because linear independent means each one cannot be written as the weighted sum of all the other vectors. Otherwise, it wouldn't be linearly independent. Okay. All right. The next concept is called vector span, or the span of vectors. So the span of a set of vectors is defined as, so if I give you a set of vectors x1, x2, xn, the span of it is defined as just the weighted sum alpha 1 x1 plus alpha 2 x2 plus so on so plus alpha n xn. It's just the same as this. You sort of can say you can sort of say this is the span. This is the span of the set of vectors. Okay. So you say if a span of 1 0 0 0 1 0 0 0 1 is just alpha 1 times 1 0 0 plus alpha 2 0 1 0 plus alpha 3 0 0 1. Span of 1 0 0 0 1 0 0 0 1 2 1 2. You can also have more than that. It's just alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 times each vector individually. Okay, you don't care about if they're linearly independent or not. It doesn't matter. We don't need to verify if they are linearly independent or not. Okay, just do the linear combination of all different vectors with different weights. Okay. The next concept is dimension of a linear space. Dimension of linear space is defined as maximum number of linearly independent vectors in the space. Okay. So let's say the space, typically this span. So this vector space, or a span of vector, is also called a vector space. Okay. For example, if I give a space which is a span of the three different vectors, which means alpha 1, alpha 2, alpha 3, time x 0 1 0 0 0 1 0 0 0 1 is respectively. You do the sum. This is the span or the space of the three vectors. So what is the dimension of the space, the linear space? Okay, so because all other, so this is the maximum number of linear independent vectors. Okay, because this one space can include many different vectors. For example, I can have, of course, I can say, well, if I said alpha 1 is 1, alpha 2 is 0, alpha 3 is 0, so yeah, it's these vectors are basically should be part of the linear space. So they should be there. And also I can do twice of that is a linear space. It should be also a vector in the space. I also twice of each of this also. And also I can do the sum of the two, okay? They also can say there are many vectors in the linear space. So you want to see how many numbers, the maximum number of linear independent in this huge amount of the vectors in the linear space. So first of all, if any derived vector, so only those, we only need to check those that created the linear space. Those ones that generated, for example, twice of that in the sum list, if they derived from these vectors, they are not going to be linearly independent, which means we don't have to verify. They are not linearly independent, those vectors. So we don't need to verify those. We only need to verify for those basic vectors, like I mentioned, that create a space, to see how many of those are linearly independent. The maximum number of linearly independent in this set, not in this big set. Okay? The reason being that because if anything is derived from there, you can always find a non-zero alpha 1, alpha 2, alpha 3, the combination such that they are not linearly independent. Okay? So here's another interpretation about why a derived vector derived from I call this basic vectors. Any vector derived from the basic vector would not be linearly independent of those the basic vectors. Okay? Another interpretation is a set of vectors are linearly independent if and only if any vector cannot be written as a weighted linear summation of other vectors. Okay? Because those derived R can be written as a linear summation of those vectors, so they are not linearly independent of those vectors. Okay. So for example, if x1, x2 is here, if I say x3 is x1 plus x2, they are not linear independent because they're derived from here. These are already linear combination of those, they're not linearly independent. So all derived vectors are not linearly independent of those that created the linear space. Okay, so the dimension of linear space is the number of the linear independent vector of those vectors that created the linear space. So we only need to verify the number of linear independent vectors of the vector that created the linear space. Okay, so for example, if I want to give a linear space which is span of x1, x2, x3, and x4. So x1, x2, x3, they are linearly independent, and x4 is derived from the x1, x2, which is 2x1 plus 2x2 plus x3 that created the last vector. Okay, so what is the dimension of the linear space? It's just 3 because the x1, x2, x3 they are linearly independent, but x4 they're not linearly independent because the last one is created by the 3, so they're not linear. It's dependent on the other 3. So the maximum number of linear independent vector is just x1, x2, x3. Okay, all 3. And generally speaking, the dimension of a span of x1, x2 to xm should be less than the number m, because at most these are linearly independent. You cannot have more than m because any other vectors derived from these vectors are linearly dependent on this vector. So this dimension should be less than the number of vectors. This is the number. This also means number of vectors that create a space. Okay. And also the dimension of the span of x1 to xm should be greater than or equal to 1. Okay, so 1 and less than or equal to the dimension of the vector. So here n is dimension of xi. For example, each x, let's say x2, for example, each one is 1, 2, 3, 4. So if here, so the n is 4. This is a 4-dimension vector. Okay, so this is m is how many vectors that created the space. This n is the dimension of each vector, which means how many numbers in that vector. So the dimension must be less than or equal to the dimension of each vector. Of course, greater than or equal to 1. Okay, right? If it's 0, which means all vectors should be 0, right? Okay. Right, I'll stop over here though. I'll talk about a little bit more mathematical background in the next video.